Dear students, the next topic is function generation, path generation, precision points, and Chebyshev spacing. Let us start with the function generation. In design of mechanism, the output link should rotate, oscillate, or reciprocate according to a specific function of input motion. This is called as function generation. In function generation, the motion of input link is correlated to the motion of output link. So consider a 4-bar mechanism as shown in figure. In this mechanism, the input link is the AB. So the input link, it will rotate through an angle of theta 2. So and it represents the independent variable x. The output link is the CD. This it will rotate at an angle of theta 4, and it indicates this output link, it is a dependent variable represented by y. So here the y, it always depends upon the value of x. Now let us assume that the input variable, so it will have the two positions, that is x1 and x2. Let x1 and x2 are the initial and final positions of the independent variable x. Similarly, y1 and y2 are the initial and final positions of the dependent variable y. So here it is assumed that there is a linear relationship between theta 2 and x and theta 4 and y. That is, so theta 2 and x and theta 4 and y. So here the output link, so it has to rotate, or it has to oscillate, or it has to reciprocate. It depends upon the type of the mechanism. If there is a slider, the output link, it will reciprocate. So the motion of this, it entirely depends upon the motion of the input link. So that function generally we call it as the function generation. Now we'll develop a relation mathematically. So we have theta 2f minus theta 2i by x2 minus x1, which is equals to r1. I will call it as a constant. Similarly, theta 4f minus theta 4i by y2 minus y1, which is equals to constant. So here theta 2f and theta 2i are the final and initial positions of angular positions of the input link, and similarly the 4f and 4i are the initial and final angular positions of the output link. So where R1 and R2 are the constants, we call it as a scale factors. If the link ratios are known, that is A by B, A by C, A by D, then a mechanism can be designed. The next one is path generation. See, in path generation, a point on a coupler link is constrained to describe a path with reference to a fixed frame. So when you take a mechanism, so it consisting of input link, it consisting of output link. In between these two, we have one more link. This link, we call it as a coupler link. Okay, so this coupler link. So I will consider one point on the coupler link. So this point, it is constrained to describe a path with reference to the fixed frame. So this path, so whenever the input motion is given, a reference point on the coupler, it will move. So the motion of that, it will be either a arc of a circle, or ellipse, or a straight line. So the motion of this, it will be either an arc of a circle, ellipse, or a straight line. So the coupler link, generally we call it as a floating link. If this path points, right, so the coupler link, it will move, right. If these path points are to be correlated with either time or with input link positions, then it is known as path generation with prescribed timing. Okay, so if this path points, okay, if these path points, if it is correlated with the input link positions, then that we call it as a path generation. Example, you can take a 4-bar linkage which is designed to pitch a tennis ball. So that is the best example for the path generation. The next topic is the precision positions or precision points. See, while designing a mechanism, in order to generate a particular function, it is usually not possible to produce mathematically exact solution. But the mechanism it fits the function at only the few points or positions, which are called as the precision points or precision positions, or we call it as accurate points. So this is a diagram which shows the two curves. Okay, one curve which represents the prescribed motion. The one more curve, it represents actual generated motion or the function. Okay, so figure shows the two curves are drawn for arbitrary function. One is actually generated, the another one is the required curve. It means a mechanism not fit an exact solution, but at few points on it, it satisfies the required function, and those points are called as precision points. So it doesn't mean, so generally when we design a mechanism, right? So we'll design a mechanism to have a motion of this, right? So this is the prescribed motion, right? It has to generate a motion of this. But in actual practice, so the mechanism it won't give the motion of the prescribed. Instead of that, it may generate a motion in this fashion. Okay, so even though if it generate a motion in this fashion, so that mechanism it will satisfy the function at some points. See, here it is satisfying, here it is satisfying, here it is satisfying, here also it is satisfying. So it will satisfy the function at some particular points. So those points generally we call it as precision points. The difference between the required motion and actual motion generated. So the difference between the required motion and the actual motion that is generated, that generally we call it as the structural error. We have one more error which is caused because of manufacturing problems. That is the tolerances in length of the links, bearing clearances, or generally we call it as mechanical error. So the next one is Chebyshev spacing or precision points. See, generally, the number of precision points is generally which is equal to number of fixed parameters that may be used in design, and it varies from 3 to 6. The best spacing of precision points for the first trial is known as Chebyshev spacing. So Chebyshev spacing of precision points is very useful in minimizing the structural error. So for n points in the range of x naught less than or equal to x less than or equal to x of n plus 1, the precision points x of j according to the Chebyshev spacing are given as xj, which is equals to a minus b into cos of theta suffix j into the pi, where xj equals precision points, x naught is nothing but the starting position, and x of n plus 1 is finishing position, that is the final position. And also the value of a, which is given as half times of x naught plus x of n plus 1, and theta j, which is given as 2j minus 1 by 2 times of small n, and the value of b, which is given as half times of x of n plus 1 minus x naught, and the value of j. J is the precision points, so it varies from 1 to n. So for more information, you can refer the textbook which is authored by me. Thank you.